Hello?
Hello, Murthy.
Ah,
Yes. Hey,
okay.
sir.
Okay.
Murthy,
Shall we start?
just continue.
Yeah, yeah,
Yeah,
yeah.
lad.
You
But
guys can hear me, right? Yeah. Yeah.
Yeah, I think Rama.
Uh, yeah, Rama probably will also join. Is he
Yeah,
joined?
we can start now while waiting.
Yeah, we can join start, I think. Yeah.
Okay, Rajeev.
Yes, sir.
Rajeev,
Yes, sir.
you can start. Okay.
Oh, oh, thank you, sir.
Rama is there already, right?
Raman, no. I've
Oh,
not.
then we have to wait for Rama. Main is Rama.
Oh, okay. Yeah, then we'll wait for a few minutes. Satono Mole.
Hey, Rama seems to be. Who is this RM? What is it? Oh, that's Ramnath. Okay. Professor Mula, if he's there, is okay. But he's an invitee only. Main
Oh,
thing is
okay.
Rama.
Oh, okay. Off is the office? Anyone there? No.
Yes, sir, I have called.
Yeah. Oh, Rama is here. Okay.
No, Rama is not there.
Rama
Yeah.
just joined.
Just joined. Okay. Yeah.
Yeah. Rama, are you
He's there. He showed his face. Yeah.
shut up face? Hey, good morning. Yeah, I think he's smiling fine. Rajiv,
Yes, sir.
yeah, you can start. Okay.
Thank you, sir. Good morning, everyone. I am Rajeev Ranjan, a PhD scholar under guidance of Professor Jason Murthy. This is the defense of the thesis title, Studies on Mechanical Behavior of Composite Solid Propellant under Uniaxial and Biaxial Loading. The motivation behind this mechanical characterization of composite solid propellant is that these propellant grain in solid rocket motors are subjected to various thermal and mechanical loads during their service.
Rajiv, can you speak a little bit louder?
Okay, sir. Am I audible?
Yeah, now it's fine.
Okay, sir. Propellant grains are subjected to various thermal and mechanical loads during the service life of solid rocket motors. This load may cause cracks in the propellant grain. Due to that, additional burning surfaces are developed, and that will lead to the combustion instability. These propellant grains are the weakest component in the solid rocket motor, so major cause of the solid rocket motor failures are linked to the structural integrity of the propellant grains. So in order to avoid such kind of failure, structural integrity analysis of these propellant grains are necessary. Also, the stress field developed in the propellant grains depends on the geometric configuration. So if a new geometric configuration has been selected for a particular mission, then a structural integrity analysis need to be done before its actual casting and firing. That will save development time as well as costs. Further, stringent requirements like a higher payload, higher velocity, higher reliability, as well as longer ranges, service lives at lower costs, further enhance the importance of a structural integrity analysis of the propellant grain. This structural integrity analysis required numerical tools for which constitutive models and failure theories based on the experimental studies are the prerequisites. The objective of this thesis was to study the mechanical behavior of composite solid propellant by conducting uniaxial tests and biaxial tests on cruciform specimens. And also the fracture surface of these uniaxially and biaxially loaded samples are conducted using a scanning electron microscope and an energy dispersive spectroscopy to understand the damage growth mechanism and failure. The scope of the work for this thesis was to conduct uniaxial and compression tests at constant displacement rates, for which DIC was utilized to measure strain. Relaxation test has been conducted at constant strain. Biaxial tests on cruciform specimens are conducted at various displacement rate ratios, and temperatures. The fracture surface under these loading conditions were uh, then studied by taking consideration of this spectrography and energy dispersive spectroscopy. This is a uniaxial tensile testing setup. 500 Newton jig roll UTM with a pneumatic rape is utilized for uniaxial testing. Two cameras facing the front and lateral surfaces of the specimen were utilized to measure all the component of strain and deformation field. The uniaxial test sample were fabricated as per the ASTM G638 Type 4 standard. Since the composite solid propellant is a viscoelastic material, so relaxation modulus is an essential mechanical properties. In order to get the relaxation modulus, relaxation test is conducted at 5% constant strain. To reach that 5% strain, a high displacement rate of 500 mm per minute is considered. This is because relaxation test is response of the material for instantaneous deformation. Then at this 5% strain, a specimen is held for 180 minutes, and then the decrease in the force with respect to time is recorded. Then using that force, stress is determined, and then using this formula, relaxation modulus is determined. Here with blue line represent the experimental data of relaxation modulus variation with time. And this relaxation, experimental relaxation data is fitted with Brownish series, which is shown here. And 11 term of the Brownish series is considered, and we observe a good mathematical fit for the experimental data. Uniaxial tensile test was conducted at 17 and 50 mm per minute. The dotted line here indicate the nominal stress, and solid line indicate the true stress. For nominal stress, instantaneous cross-section area is used, whereas for true stress, instantaneous cross-section area is required, and that instantaneous cross-section area we measured by measuring the instantaneous width and thickness of the specimen using DIC. Here it can be the first plot here indicate the failure of the material, stress strain response up to the failure, and this plot is just a zoomed in view of this stress strain response up to the failure. This plot is up to 50% strain to see the initial behavior of the material. It was observed that the stress strain response was non-linear, and it was depending on displacement rate. Tensile modulus and yield stress was increasing with increasing displacement rate. Poisson ratio is also an essential mechanical property for structural integrity analysis, and it was determined during uniaxial tensile test. Poisson ratio, since there was two camera, Poisson ratio we calculated on both the lateral as well as the transverse surface, and it has been observed that the Poisson ratio variation was same on both the surfaces as well as for all the displacement rate. It was close to each other. At the beginning of loading, it was 0.5, and then as the strain was increasing, this Poisson ratio was decreasing. Since the reason behind this is as the material deformed during loading, the bonds which is responsible for contracting the lateral and transverse surface of the specimen that breaks, and then its capability to contract reduces, leading to reducing Poisson ratio as the strain is increasing. We determine in the dilatation during uniaxial tensile test, this finite strain dilatation formula is used for that. This response here shows the dilatation response up to the failure, whereas this is the zoomed in view of the dilatation up to the 50% strain. Since in composite solid propellant, the matrix are polymer material, which is nearly incompressible, and the solid particles are rigid, comparatively rigid, so they doesn't undergo any volume change. So whatever the dilatation we observed, we can say that that is coming from the vacuum hole formation in the material. So based on that, we divided the dilatation response into the three regions. So first region was where dilatation was nearly zero, that was up to 2% of the strain. So we said that in this zone, there is no detachment of the solid particle, there is no vacuum hole formation. In the second region, the dilatation was increasing at an increasing rate. So in this region, the vacuum holes are getting formed because of the strain in the material, and there are some existing vacuum holes which formed in the beginning, I mean after 2%, strain, and that is growing in size. So two phenomena, that the growing size of the vacuum holes as well as the formation of the new vacuum holes is happening in the second region. That's why dilatation is increasing at an increasing rate. In the third region, we observed that the dilatation was increasing at a constant rate with strain, and this is because after a certain strain for this material, it was around 20%. There is no new vacuum hole formation, and only the existing vacuum hole growing in size, leading to increase of dilatation at a constant rate. We conducted uniaxial compression test, and for this, during uniaxial compression test, to measure strain, 3D DIC is utilized. This is because the 2D DIC is suitable only for a planar measurement of a strain or deformation field of a planar section, which undergoes planar deformation without large out of the plane deformation. However, in the compression test, although the surface was plane in the beginning of the loading, but as the load applied there due to the barreling, and also due to the barreling, the surface become curved, and also there is large out of plane deformation during compression loading, compressor testing. So these two, due to these two reasons, 2D DIC is not suitable for measuring strains during uniaxial compressive loading, and that's why 3D DIC is utilized. For 3D DIC, two cameras need to be placed at an angle as shown in figure here. And one of the problem in doing compression testing is the barreling of the specimen. In order to minimize the barreling, lubricants has been placed between the compression plates and the specimen surfaces. However, it was observed that we was not able to eliminate it completely. This is a compressive stress strain response. Here, first plot shows the nominal stress versus nominal strain plot, and this is true stress versus 3D DIC strain plot. There was a large difference in the nominal versus true stress responses. And similar to the uniaxial tensile loading, here also it was observed that the response was dependent on the displacement rate, and it was nonlinear. During compression loading, also dilatation and Poisson ratio were determined. Same finite strain dilatation formula and formula for Poisson ratio, same formula which was used for tensile loading is used for this compression loading also. And we observed that around up to 10% of the strain dilatation was nearly zero, and corresponding Poisson ratio was close to 0.5. However, after that, it was increasing both dilatation as well as the Poisson ratio, and it seems that the reason behind this is the barreling and damage in the material. In order to see that how this compression loading is affecting the material, so we have taken the ACM images of the surface of the specimen. This first image is before loading, and the second one after the loading. And we observed that in the virgin material, the solid particles were well coated within the matrix. However, when this compression loading are acting on the material, this deviating is happening, which was visible in the form of voids. We conducted biaxial test, and the motivation behind conducting biaxial tests there are two reasons. First is the propellant grain in the solid rocket motors are subjected to multi-axial stress field. So conducting biaxial test will be a more accurate representation of the expected behavior. Secondly, the CSP, when they cast as grain in solid rocket motors, are quasi-isotropic in nature. However, upon loading, micro voids formed in that, and it become anisotropic. And biaxial test is essential to characterize anisotropic material. So these two reasons are necessary. Due to these two reasons, we conducted the biaxial test on composite solid propellants. In literature, there are various techniques to do the biaxial test, like bulge test, combining tension and torsion, combining bending and in-plane, as well as combining axial load and internal pressure, or using a cruciform specimens. Out of these techniques, biaxial testing on cruciform specimen is more promising, because here different stress on the sample can be obtained by altering the displacement or load ratios in two mutually perpendicular directions. In order to do the biaxial test, the first step is to design a cruciform specimen for composite solid propellants, because there was no standard geometry for that. In order to get the optimized geometry of the cruciform specimens, we consider the two design criteria. First one was that the stress should be maximum at the gauge area so that the specimen fails there. That is necessary because then only we will be able to capture the behavior of the material up to the failure. Otherwise, one of the biggest problem in conducting biaxial test is the failure of the arm of the specimen. In order to avoid it and fail the material at the gauge section, stress should be maximum at the gauge section. And the second design criteria was that there should be homogeneous stress and or strain distribution at the gauge section. This is the flowchart for the fabrication of the cruciform specimen. So first, copper titanium cruciform cutter was used to cut cruciform specimen out of the CSP plate, and then using CNC drilling machine, the center section of the material is removed. This is the final shape of the cruciform specimen. Biaxial tensile tests were conducted on a 5 kN BIS biaxial testing machine, which contains a hydraulic power pack, a loading frame on which 4 double-acting hydraulic actuators is mounted, and each hydraulic actuator contains pneumatic grips which hold a specimen during the experiment. Since we conducted experiment at controlled temperatures, so environmental chamber was there to do that. All 4 actuators contain load cells and displacement sensors. So in this study, the average of load measured by 2 load cells along each direction is considered for determining stress at the gauge section. Since in the cruciform specimen there is no clear resisting area, so to calculate the stress. So stress cannot be estimated directly as load per unit area. In order to calculate the stress, the fraction of applied load which bypasses the gauge section need to be determined. And to do that, we use the FES software Abacus. Since the geometry and loading was symmetric, only 1/8 portion of the specimen is modeled, and symmetric boundary conditions were used along with the hyperviscoelastic model. Hyperviscoelastic model were considered for this FE analysis. So based on this FE analysis, we observed that the bypass factor for equibiaxial loading was 17.6% in both x and y direction, and that of biaxial loading, for the biaxial loading ratio of 0.5:1, it was 11.11% in x direction and 20.05% in the y direction. This FE analysis we also conducted by considering linear viscoelastic model, and nearly equal bypass factor we observed. This is the stress strain response for equibiaxial test, and this plot here is the stress strain response up to failure for 20 degrees centigrade. This is the zoomed in view of this plot up to 50% strain, and this is the equibiaxial test response at 55 degrees centigrade. For each test condition, at least 5 experiment has been conducted. For both the temperature, material response was significantly depending on displacement rate, and there was a large decrease in failure strain when temperature was increased from 20 to 55 degrees centigrade. We also observed that the sigma stress strain response is linear up to 4% strain in both x and y direction. During biaxial loading of displacement rate ratio of 0.5:1, we observed these test responses, where again the dependence of displacement rate as well as the temperature was there. Here also, with increase in temperature, there was large decrease in the failure strain. However, in this for this particular displacement rate ratios, it was observed that the stress strain response is linear only up to 1% strain in x direction, and it was the same value as we observed during equibiaxial, which is 4% strain in y direction. This is happening because since displacement rate in y direction is double as compared to that of x direction. So materials are getting strained at a faster rate in y direction, and when actual visible damage effect start coming in this stress strain response, that time the strain seems in y direction is around 4%, but since displacement rate in x direction is less, that's why in the material becoming non-linear at the from the 1% strain itself. Also, it was observed that the stiffness in x direction is very high as compared to the y direction. Generally, in polymeric material or viscoelastic material, as the displacement rate increases, stiffness increases. However, in this case, since this displacement rate is double in y direction compared to the x direction, that higher displacement rate is causing higher strain in y direction, and that strain is acting as a pre-strain for the x direction, and that lead, that is the reason behind higher stiffness in x direction as compared to the y direction. In order to see the effect of stress field, uniaxial and equiaxial test response has been compared. This plot shows the this stress and strain response up to the failure for both uniaxial and biaxial loading, and this is the zoomed in view of this particular plot up to the 50% strain. And we observe that the uniaxial and biaxial stress strain responses are similar qualitatively. However, their quantitatively it varies a lot. So this equiaxial, during equiaxial testing, the yield stress was 25 to 47% higher as compared to the uniaxial test. This is happening because in uniaxial loading, one of the surfaces is free. Load is applied in one direction, another surface is free to deform. So material is offering less resistant. However, in biaxial loading, it is loaded in both the directions, so there is no free surface. So material is offering more resistance to deformation, leading to a higher yield stress. Also, it was observed that the failure strain during the equiaxial loading is 50 to 70% lower than that of the uniaxial loading. This is happening because in composite solid propellant, when it is loaded, the failure mechanism is that the vacuum holes are formed due to detachment of the solid particle from the matrix. Then this vacuum hole size will grow, and this phenomena will occur at various places in the material, and then these various vacuum holes coalesce together to form the macro crack. The process of coalescence this crack accelerate in the presence of higher triaxiality. During biaxial loading, triaxiality is higher than that of uniaxial. That is the reason of having lower failure strain during equiaxial loading as compared to the uniaxial loading. We studied this fracture surface for both the uniaxial and equiaxial loading, which is shown here. This all the fractographic images shown here is taken for 20 degrees centigrade at various displacement rate of 1, 50, and 1000. And this first three graph, these micrographs are for uniaxial loading, and this is for equiaxial loading conditions. We observed that the for both uniaxial and equiaxial that the cavities are formed on the fracture surfaces, and this is because of the detachment of the solid particles due to duetting. This is the comparison of the fractographic images are taken for equiaxial loading as well as for the displacement rate ratio of 0.5:1 at different displacement rate. We did not observe any notable difference between the micrographs for these conditions. The same thing has been done here. We have taken fractographic images for 55 degrees centigrade, and in between this, with respect to the displacement rate as well as the for displacement rate ratios, there was no significant difference. However, compared to 20 degrees centigrade, here the fracture surface was smooth. This is because of failure strain at 55 degrees centigrade is very less compared to that of the 20 degrees centigrade. In literature, it has been observed that the fracture mechanism of the CSP may change from the tearing and duetting of the AP particles to the fracture of the AP particles as the strain rate increases, in order to see whether in this case, with increase in displacement rate, where this particular phenomena of fracturing the solid particles is observed or not, we have conducted the energy dispersive spectroscopy. So in energy dispersive spectroscopy, the chlorine map indicates the AP particles, and we have considered the corresponding micrographs to observe the AP particles. And in this study for this particular CSP, it was observed that even at the highest displacement rate, which we considered as 1000 mm per minute, there was no fracture of the AP particles. In the visible outputs in the form of publications, and we presented this work to 3 different conferences. These are the references. I want to thank HEML for providing these material samples and Armanet Research Board for funding the studies. I also thank SAFE. I also want to thank Professor Rajeev and Siva Prasad for their help in providing the high-speed camera. Thank you.
Okay, thanks. Questions from the audience? Bala? Yeah, Bala is not here. Morty?
Yeah, no questions
who-
from my side. I just got a message from Bala. It's okay. Yeah.
Okay, and then the reviewers' comments? Who is
P. Ramakrishna, reviewer. Yeah.
okay, Rama?
Uh, a good presentation. Rajeev, can you go to slide 17 that you showed? Here, what is the assumption that you're making? Are you making the assumption that it is a particulate composite, the solid propellant, or you are making it as a homogeneous material?
I'm taking it a homogeneous material, and
In
considering
that
the
case,
hyperviscoelastic model.
okay. In that case, if what are the properties of the composite material that the particulate composite material, let's say some parameter is something, only then you will be allowed to assume this. Is there something like that? I don't know if you
Since in
understood.
the this composite solid propellant, since it is a particulate composite, and the beginning it can be assumed as a quasi isotropic. So that's why we consider as a isotropic material, and its viscoelastic nature has been viscoelastic nature as well as the nonlinear nature is taken into consideration by taking the hyperviscoelastic model.
Okay. Fine. The other thing is, I had asked you some questions in my this
Yes,
thing.
sir.
Please show me that this thing that.
Okay. So first question was to provide a clear rationale why biaxial tests are more suitable. So
Yes.
In the solid rocket motors, these various loads, various stresses, it is shown here that one of that is the longitudinal stress, and the section view of shown here, which is where radial stress as well as the hook stress acts. So in this propellant grain, always there is a combined stress field. So that's why biaxial tests, which simulates the combined stresses, is more essential for studying the CSP behavior. So in the thesis, we rewrite this motivation, whatever the motivation we gave.
Not we, you.
Sorry,
This is not joint.
Yes.
Murthy, I think, has got his PhD long back.
Yeah, 20 years.
Okay, next. Something was there, no?
Yes, sir. Another question was that I proposed some future works. So it was mentioned it will be better if it can be explained how it will be meaningful to the solid rocket propellant industries. So for each future work, I added this how it can be meaningful. So first was to conducting Excel tensile and compressive test at different temperatures.
Mhm.
So the data, the mechanical properties which will be obtained for this all different temperatures, it will be crucial for designing the SRM because their operational temperature.
Suppose I say I don't want to do at higher temperatures and I do at lower temperatures. Is that fine or is it bad? I don't have a facility of high temperatures. I only do at low temperatures.
Okay, so though a few properties like stiffness will increase at lower temperatures as well as it will be low for higher temperatures. So that difference in the properties will be there. And generally at lower temperature, failure strain also decreases.
Uh-huh.
So
So that is why I am asking you. If I do it only at lower temperature, can I say it is safe at higher temperature?
uh, I think no, sir. Unless until it will be, it is observed how much difference in the properties is there, we can't say.
Okay.
There
Okay.
are few propellants where that show very large variation in properties with respect to temperature.
Okay. Fine. Okay. I'm done, Louis.
Okay.
Ah, okay. Murthy here. I want to ask a few questions as follow up.
Okay. Yeah.
Yeah, one is Rajiv, the slide number 17 part, which Rama
Yes,
asked,
yes.
right? In that part, where did you get these properties from for doing this analysis?
So for hyperviscoelastic model, this hyperelastic properties in Abacus, it has to feed in the form of the nominal stress response.
Yeah,
So I
but where did
used
you get that response from?
we conducted in Excel test, no sir. So that response I fed to Abacus.
That's essential to mention. Yeah. Okay. Yeah. So the other part of it is the last slide, which Rama was asking. Hello?
Yes, sir. Yes.
Yeah, but the question really is that if lower temperature is lower temperature bad or is it higher temperature which is bad when it comes to propellant? Bad in the sense leading to earlier failure.
Sir, for this particular CSP which we studied here, this with increase in temperature, there was huge decrease in the failure strength. So for this particular propellant, it was higher temperature actually, which is bad.
Okay, okay. So so I cannot look at lower temperature and say this is the most conservative case. So
Uh, no, sir. Unless until at least in Excel test a different temperature, it is there. It will be difficult to make a decisions.
okay, so that's it from my side.
Okay. Thanks. Anyone else? Questions? If you don't have, yeah, I can ask students to log out. Thank you all.
Thank you, sir.